And so what's some of the disciplines that you're aiming at?
Well, so since our institution covers most areas of science and engineering, in fact, there was a goal that we would cover all disciplinaries that we would, universities conducting research thereof. So this covers everything from structural dynamics, fluid dynamics, life sciences, material science, robotics, everything that we are very good at as an institute. And but where technical computing had been underutilized because of the fact that there were much access or to be used. So that's sort of scalability in a different sense than capability. This is scalability in terms of providing access throughout campus to these high resources in a very easy to use way.
Yeah, I remember, of course, you probably don't know this story, but one of the ways I became aware of this is I got this piece of email, and it had the list of all the applications that we plan to run. And it was a little bit longer than most lists for supercomputing centers, and it covered all these disciplines because you had Gaussian and CFD as well as a broad range of stuff. And I go, wow, that's kind of interesting. It's a big long list. So you had an applications team, and you had some interesting insights about, what does it take to develop applications for these kinds of systems, and how can you make it easier for people in designing and clustering?
Yeah. So basically, the users are very broad. The user base in terms of experience. Some are very extreme experts. They have run big simulations on thousands of processors on big machines like yours, to novices who have just started programming their workstations. And these disciplines, like you said, range from material science to fluid dynamics, mechanics, some new applications like social sciences, doing social simulations. And then the type of applications range from everything from homegrown code that's been sort of inherited over a number of years in the lab to people exploiting ISV applications. And of course, that's the mission as a center to support these ISV applications as well. So we're faced with this amazing diversity. And then to make things easier for people to access the challenge.
Yeah, so you have notions about, I guess a single sign-on and an image on the file system and stuff. So how many people use this and what's it like? Is it busy?
Well, the system is extremely busy at the moment, despite the fact it has over 10,000 CPU cores. We have 10,000 people. So.
Our factories are standing by.
Okay.
Do you want to be in the 5 thing? Just
have to raise the cap.
Yeah.
Work my institution to bank. So
yeah, there you go. Yeah, banks is okay.
My sister worked for an investment company. Maybe.
There you go.
What's the question? Yes,
how many people use it? How busy it is?
So the ultimate goal was to provide access to every single individual on campus, such that they have accounts of different levels, of course, because depending on their skill levels. But practically everybody has an account, and practically everybody can use the basic services. Mm-hmm. There are some users who use higher-end services, and these are a much smaller number, maybe than 1,000 people. But still, the previous system, which only a few handful, maybe a few users, the user base has grown, as well as the variety of users has grown as well.
So the style is a little different than other supercomputing centers. Are there things that are like changes that you saw in the curriculum, or the way faculty think about it, or the way students do things that came about? Can you point to and say, hey, this is different because of this, the fact that I've exposed this to so many people?
Yes. Certainly the difference is, of course, we have quite traditional supercomputing users, so obviously people using this for very large-scale simulations. But what we see differently are we're getting increased inquiries in the educational space, and people, for example, doing classrooms teaching theoretical teaching theory. For example, people teaching molecular orbital shredding equations. And then they would come and say, well, we'll do a lab course, which is hard on our existing lab machines, but can we do it on TUBAME? And I say, yeah, it's on everyone has a cap. We do it, all the IC applications are all set up. You
instant on. They can just
Yeah, and so we're seeing an increasing number of people who are exploiting TUBAME for educational purpose, incubating the next generation of these users. I think the second difference it has made is it's made access to the external partnerships much easier. So we're getting a tremendous number of inquiries from people who are partnering with outside, say, commercial institutions. And they are desiring to use our machine because of the sheer scale, and that are not available to their particular institutions.
So where are you today, Skitty? You're in the top 10, right?
Well, yeah.
Depends on the day, right?
Depends on
the bar keeps moving up is the problem.
Well, that's a big challenge. It's a pretty tough world out there.
Yeah.
Of course, we reach our goal. But we are certainly as an open university machine, we are the fastest in the world still. Yeah. And then even as an open machine with public access to many users' accounts, we are also fast. So in a sense, we have made qualitative differences where people have the motivation. I mean, after all, why do you use a supercomputer? Right? Because it's not. There are things you can't do on your laptops. There are things you can't do on your small clustered lab, and we need to make these qualitative differences very visible. Yeah. Otherwise, people will not be very.
So you had a couple of projects you were showing me on your laptop. I don't know, maybe if you try to plug that in here. We're going to plug a laptop into demo 1 for the folks in behind the curtain there. I know we're going to spring a surprise on you and test your agility because we didn't warn you ahead of time.
This is totally unplanned.
Totally unplanned. We're going to plug that in. And I'll just talk a little bit about the cluster itself. So what Satoshi did was build a cluster a bit different than conventional clusters of up to time, which typically were a large number of small nodes. What he decided to do based on application analysis was to build fairly large nodes. So all the nodes are 32 and some are 64 gigabytes. 8 socket nodes. There's 655 8-socket AMD Opteron machines, and they're connected to a new storage device from Sun. 55 of those, which are 24 terabytes a piece of storage, using 2 InfiniBand networks. And so it's an interesting cluster because despite the fact that it was at one point 7th in the world or so, it's actually very simple compared to other clusters of its scale. The number of components and the amount of pieces of technology involved were not in the thousands to go build this. And it's probably a good thing because Satoshi had kind of a limited space and plant to actually do this, and the cluster is actually built on 2 floors, and Satoshi has technology and cable between them to try to get the topology of the network. But it's a pretty interesting cluster from that regard. It's an example of enterprise technology, so what we did with him was actually take technology intended for the enterprise and build a large cluster out of it. And as a consequence, it has some interesting properties of remote management and upgradability and all that. And certainly you can talk about how that is, because one of the things that he wanted was to actually get a fairly reliable and highly available cluster as well for all student use. So among top 10 clusters in the world as well, it has really exceptional statistics as far as its availability and benchmarking. So are they able to get this up, or is this they're working on it?
They're working on it, I think. Oh, yes.
There we go.
Okay, thanks. You have a great team here, John.
Yeah. So this many people behind the curtain do everything.
Yeah. Time to deliver.
Yeah.
So I'll show you maybe 2 or 3 applications that are making quality differences. One is this is an application that had been that previously ran on the Earth simulator, which was the number 1 machine in the world at the time, built by, and it's a humongous $700 million machine. Now, the point being that now it runs readily on our machine. Now it's fairly easy for its Earth magnetic sphere Earth problem. As we know, at Earth, why do we have North Pole and South Pole? That's because there is